Welcome! In this video, we'll be tackling LeetCode problem number 149, titled Max Points on a Line. This problem challenges us to determine the maximum number of points that reside on the same straight line. It's an excellent opportunity to sharpen our skills in geometry and hash maps. Let's dive in and explore this problem step by step. In this problem, we are tasked with finding the maximum number of points that lie on the same straight line in a 2D space. The input is an array of points, where each point is represented as a pair of integers, x_i, y_i. The goal is to determine how many of these points can align perfectly on a single straight line and return that number. For example, if the input is 1, 1, 2, 2, 3, 3, the output is 3 because all 3 points lie on the same straight line. This problem makes use of geometric principles like slopes and collinearity to evaluate the alignment of points on a plane. To explain further, in the first example, the 3 points, 1, 1, 2, 2, 3, 3, align because the slope between any 2 points is consistent. This means they all lie on the same line, so the maximum number of points is 3. In contrast, for the second example, we have 6 points, 1, 1, 3, 2, 5, 3, 4, 1, 2, 3, 1, 4. Here, not all points align on a single line. However, there is a subset of 4 points, 1, 1, 2, 3, 3, 2, and 1, 4, that do align. The largest number of points forming a single straight line in this case is 4, and that becomes the output. Now, let's consider the constraints and some key edge cases. The number of points can range from 1 to 300, and each point is represented by exactly 2 integer coordinates. These coordinates can have values between -10⁻4 and 10⁻4, and all points in the input are guaranteed to be unique. For edge cases, if there is only one point, the output is trivially 1 since a single point can always be considered to lie on a line. Another interesting scenario is when all points form a horizontal or vertical line. For instance, points like 1, 1, 1, 2, 1, 3, 1, 4 all align vertically along x equals 1, so the output would be the total number of points, which is 4 in this case. Finally, in cases where the points form multiple lines, the challenge is to identify the line that contains the maximum number of points. This requires calculating slopes between pairs of points to determine collinearity. However, care must be taken to handle edge cases like vertical lines, which have an undefined slope, or overlapping points, which share the same coordinates. To optimize the solution, we can use a hash map to store slopes and their corresponding point counts. This approach helps efficiently track the alignment of points while avoiding precision errors and ensuring the correct line is identified. To solve the problem of finding the maximum number of points that lie on the same straight line, we can explore different approaches, starting with a brute force method. The intuition behind this naive approach is that any 2 points uniquely define a straight line. By iterating through all possible pairs of points, we can calculate the line equation for each pair and then count how many other points lie on that same line. The steps involve calculating the slope of the line connecting each pair of points, checking how many additional points share this slope relative to one of the 2 points, and tracking the maximum count across all pairs. However, this approach has a significant limitation due to its time complexity of O(n³), which arises from the nested loops required to iterate over pairs and count points. It is also memory efficient with O(1) space complexity, but the cubic time complexity makes it impractical for larger datasets, especially in competitive programming scenarios. Thus, while conceptually simple, the brute force approach is inefficient for this problem. To address the inefficiency of the brute force method, we turn to an optimized approach that leverages slopes and hash maps. The key insight here is that points lying on the same line share the same slope relative to a fixed anchor point. Instead of checking all pairs, we can fix one point at a time and calculate the slopes of lines connecting this anchor point to all other points. By storing these slopes in a hash map, where the keys are the slopes and the values are the counts of points, we can efficiently determine the number of points that lie on the same line for each anchor. This approach involves reducing the slope to its simplest fractional form, ensuring that duplicate slopes are correctly handled. Additionally, it accounts for edge cases such as vertical lines, where the slope is undefined, and overlapping points, which share the same coordinates. With a time complexity of O(n²), as we compute slopes for all pairs of points, and a space complexity of O(n) for the hash map, this method offers a significant performance improvement over the brute force approach. While an alternative approach could involve directly calculating line equations, this is less efficient due to floating point precision issues and potential hashmap collisions, making the slope-based method the preferred choice. The optimized approach using slopes and hashmaps is chosen as the most effective strategy to solve this problem. The critical insight is that by reducing the task to counting slopes relative to an anchor point, we avoid computationally expensive operations like calculating full line equations. This makes the solution both faster and simpler to implement. Iterating through all points as anchors and leveraging a hashmap to store slopes results in a time complexity of O(n)², which is optimal given the constraints of the problem. Furthermore, the use of reduced fractions for slopes ensures the solution handles edge cases, such as duplicate points or vertical lines, with correctness and precision. While this method does require additional memory, with a space complexity of O(n) for the hash map, the trade-off is well worth the significant reduction in time complexity, from O(n)³ in the brute force approach to O(n)². This balance of clarity, performance, and robustness makes the slope-based approach ideal not only for competitive programming but also for real-world applications where efficiency is critical. The problem max points on a line asks us to find the maximum number of points that lie on the same straight line, given a set of points in a 2D plane. To solve this, we start by addressing edge cases. If there are fewer than 2 points, the result is simply the number of points provided. 0 points means no line exists, and 1 point can be considered to trivially lie on any line. Next, we iterate through all the points, treating each one as an anchor point. From there, we calculate the slope that each pair of points forms, using the anchor as one of the points. The slope is what uniquely identifies a line, and this is the key to determining how many points share the same line. To compute the slope between 2 points, we use the formula, the difference in y coordinates divided by the difference in x coordinates. However, to avoid issues with floating point precision when calculating slopes, we store slopes as reduced fractions instead of using division. This involves calculating the differences in x and y coordinates, simplifying these differences using their greatest common divisor, and then storing the slope as a pair of integers, the reduced numerator and denominator. For instance, a slope calculated with dy and dx is stored as dy/gcd, dx/gcd. Special cases like vertical lines, where the x coordinates are the same, dx equals 0, are represented as 1, 0, and horizontal lines, where the y coordinates are the same, dy equals 0, are represented as 0, 1. With these unique representations, we avoid inconsistencies. To track how many points share each slope for a given anchor, we use a hash map. The keys in this hash map are the reduced slopes, and the values are the counts of points that align with each slope. Additionally, we keep track of duplicate points, as overlapping points inherently share all slopes with the anchor point. For each slope in the hash map, we compute the total number of points on the line that the slope represents. This includes the count of points sharing the slope as well as any duplicate points. If this total exceeds the current maximum for the anchor point, we update the global maximum result. After repeating this process for all points as anchors, the overall maximum number of points on a single line is returned. The algorithm's core insights include ensuring slope uniqueness by storing them as reduced fractions, which prevents errors caused by floating point precision. The use of a hash map to count slopes ensures that we can efficiently track and compare slopes in constant time per calculation. Normalizing slopes with the greatest common divisor guarantees a consistent and unique representation for any line. Explicitly handling duplicate points ensures that edge cases, such as points overlapping, are correctly accounted for. Finally, by iterating through all points as anchors, we systematically consider every potential line in the dataset. This systematic approach of iterating through all points as anchors eliminates the need for additional data structures while ensuring thorough coverage of every possible line. The algorithm relies heavily on 2 key data structures, the hash map and a few supporting variables. The hash map stores slopes and their frequencies for each anchor point, with the key being the reduced slope pair and the value being the count of points sharing that slope. Supporting variables include duplicate_count, which tracks the number of points overlapping with the anchor, max_points_for_anchor, which tracks the maximum number of points on a line for the current anchor, and global_max, which stores the overall maximum for the entire input. From a complexity standpoint, the algorithm processes each point as an anchor in the outer loop, and for each anchor, computes slopes for the remaining points. The GCD computation is logarithmic in the smaller of dx and dy, leading to a total time complexity of n squared asterisk log n. The space complexity of the algorithm is proportional to the number of slopes calculated for each anchor, which can be at most the total number of points. This results in an O(n) space requirement for the hash map. To further optimize the algorithm, we can avoid redundant slope calculations by noting that the slope between points I and j is equivalent to the slope between j and I. This reduces unnecessary work. Additionally, using integer arithmetic to represent slopes not only ensures precision but also reduces computational overhead compared to floating point operations. Together, these optimizations make the algorithm robust and efficient for determining the maximum number of points on a single line in a 2D plane. Here, we begin by importing two essential modules, defaultdict from the collections library for handling dynamic dictionaries, and GCD from the math library to compute the greatest common divisor. The solution class contains the maxPoints method, which takes a list of points as its input. If the total number of points is 2 or fewer, the function simply returns the length of the list, as any 2 or fewer points will always lie on the same line. Next, we define a helper function called slope that calculates the slope between 2 points, p1 and p2. The difference in x coordinates is stored as dx, and the difference in y coordinates as dy. If dx is 0, it represents a vertical line where the slope is treated as 0, 1. Similarly, if dy is 0, it represents a horizontal line with a slope of 1, 0. For all other cases, we compute the greatest common divisor of dx and dy using GCD and reduce the slope to its simplest form by dividing both values by the GCD. After defining the slope function, we initialize max_points to 0, which will track the maximum number of points on a single line. The outer loop iterates over each point in the list, treating it as the starting point for slope calculations. For each such point, we initialize a defaultdict called slopes to count the occurrences of each unique slope, and a variable duplicate to handle any duplicate points, starting with a value of 1 to account for the current point itself. The inner loop then iterates over all remaining points in the list. If the current point being compared is the same as the starting point, we increment the duplicate counter, as these represent overlapping points that always lie on the same line. Otherwise, we calculate the slope between the 2 points using the slope function and increment its count in the slopes dictionary. After processing all points for the current starting point, we update max_points by taking the maximum value between its current value and the sum of the highest count in the slopes dictionary and the duplicate counter. This ensures that all points sharing the same slope, along with any duplicates, are considered. Finally, after evaluating all points as potential starting points, the function returns max_points, which represents the maximum number of points that can lie on a single straight line. Here, we start by defining the maxPoints method, which takes a 2D array representing the coordinates of points on a plane. If there are 2 or fewer points, the maximum number of points on a line is simply the number of points, so we return that directly. Otherwise, we initialize a variable maxPoints to track the overall maximum points we can find on a single line. Now, we use a nested loop to iterate through each pair of points. For the outer loop, we fix one point, and for the inner loop, we compare it with every subsequent point. We also create a hash map called slopes to count the frequency of unique slopes between the fixed point and all other points. Additionally, we introduce a duplicate counter to handle cases where points are overlapping, as overlapping points share the same coordinates. In the inner loop, if 2 points are duplicates, we simply increment the duplicate count. Otherwise, we calculate the slope between the 2 points. To ensure accuracy and consistency, we calculate the greatest common divisor, or GCD, of the differences in x and y coordinates and normalize the slope by dividing both differences by the GCD. Finally, we represent the slope as a string, combining the normalized x and y values to handle sign consistency and avoid floating point precision issues. The normalized slope is then added to the slopes map, with the count increment for each occurrence. Once all points have been compared with the fixed point, we determine the most frequent slope by finding the maximum value in the slopes map. This frequency represents the maximum number of points that align on a single slope with the fixed point. Adding the duplicate count ensures that overlapping points are included in the total. We then update our maxPoints variable to store the maximum value found so far. After iterating through all pairs of points, the method returns max points, which represents the maximum number of points that lie on a single straight line. Finally, we include a helper method, GCD, to calculate the greatest common divisor using the Euclidean algorithm. This method ensures that slopes are normalized effectively, making the solution both accurate and efficient. To solve the problem of finding the maximum number of points that lie on the same straight line, we start with the example input, 1 1, 2 2, 3 3. First, we initialize max_points to 0, which will keep track of the highest number of collinear points we identify. Now, we begin the outer loop with the first point, 1 1. For this point, we create an empty dictionary, slopes, to count occurrences of each slope, and we set duplicate to 1 to account for the starting point itself. Moving to the inner loop, we compare 1 1 with the next point, 2 2. By calculating the differences in x and y coordinates, dx is 1 and dy is 1. Using the greatest common divisor, GCD, the slope is simplified to 1 1, and we update slopes to reflect 1 point on this slope. Next, comparing 1 1 with 3 3, the differences dx and dy are both 2, and using the GCD of 2, the slope is again 1 1. We increment the count for this slope and slopes to 2. As we continue, the total number of points on the slope, 1 1, for the first point, 1 1, is calculated as 2 plus duplicate, which equals 3. This becomes our current maximum, so we update max_points to 3. Next, we move to the second point, 2 2, in the outer loop, resetting both the slopes dictionary and duplicate to their initial values. Now, we only compare 2 2 with 3 3 in the inner loop. Using the same slope calculation process, we find that the slope between these points is 1 1, and we increment its count in slopes. The maximum points for this slope, including the duplicate point, 2 2, is 1 plus duplicate, which is 2. However, since max_points is already 3 from the previous iteration, it remains unchanged. Finally, the function concludes with an output of 3 as the maximum number of points on a straight line for this example. Now, let's analyze another example with input points, 1 1, 3 1, 5 1, 7 1. These points are horizontally aligned. We start by initializing max_points to 0. Beginning with the first point, 1 1, we create an empty slopes dictionary and set duplicate to 1. In the inner loop, comparing 1 1 with 3 1, we calculate the differences dx and dy as 2 and 0, respectively. This results in a horizontal slope of 1 0, which we add to the slopes dictionary with a count of 1. Then, comparing 1 1 with 5 1, we find the same slope, 1 0, and increment its count to 2. Finally, comparing 1 1 with 7 1, the slope remains 1 0, and its count increases to 3. Adding the duplicate point, the total points for this slope become 3 plus duplicate, which equals 4. At this point, we update max_points to the maximum of its current value and the points calculated for the slope, 1 0, which gives max_points equals 4. Next, we proceed to the second point, 3 1, in the outer loop, resetting slopes and duplicate as before. In the inner loop, we compare 3 1 with 5 1 and 7 1. The slope calculation results in 1 0 for both cases, and we increment the count for this slope in slopes. Including the duplicate point, the maximum points for this slope is 3, but since max_points is already 4, it remains unchanged. The function ultimately returns 4 as the maximum number of collinear points for this example. In the next example, the input points are 1 1, 1 2, 1 3, 1 4, which are vertically aligned. We start by initializing max_points to 0. For the first point, 1 1, we initialize an empty slopes dictionary and set duplicate to 1. In the inner loop, comparing 1 1 with 1 2, the differences dx and dy are 0 and 1, respectively. This results in a vertical slope of 0 1, which we add to slopes with a count of 1. Comparing 1 1 with 1 3, the slope is again 0 1, and its count increases to 2. Finally, comparing 1 1 with 1 4, the slope remains 0 1, and its count becomes 3. Including the duplicate point, the total points for this slope are 3 plus duplicate, which equals 4. We then update max_points to 4, which is the maximum number of points on a straight line for this set of input points. Since no more outer loop iterations provide a higher value, the function concludes with a final output of 4. This completes our walkthrough of the solution, showcasing how the algorithm efficiently calculates slopes and tracks the maximum number of collinear points for various input configurations. In this algorithm, we aim to determine the maximum number of points that lie on the same straight line. To achieve this, we iterate over all possible pairs of points. If the total number of points is n, the outer loop will iterate through each point once, running n times. Within this outer loop, the inner loop considers all points that come after the current point. This means, for each iteration of the outer loop, the inner loop will run for the remaining points, leading to a total of n1 plus n2 plus 1 iterations. This sum is equivalent to the first, n1, integers, which simplifies to n1 asterisk n/2. This gives us an overall time complexity of n squared for the nested loops. For each pair of points, the slope between them is computed using the GCD function. Since the GCD operation depends on the values of dx and dy, which are derived from the point coordinates, we treat its complexity as 1 for simplicity. Additionally, during the inner loop, we update a dictionary to store slopes, and these dictionary operations, such as insertions and lookups, also average out to 1. Now, when we combine all these steps, the dominant factor in the time complexity is the nested loops, which results in an overall time complexity of n squared. Shifting our focus to space complexity, for each iteration of the outer loop, we use a dictionary to store the slopes between the current point and all other points. In the worst case, there can be up to n1 unique slopes for a single point, requiring n space. However, this dictionary is cleared and recreated for each iteration of the outer loop, so the space usage is not cumulative. Beyond the dictionary, the algorithm also uses variables like max_points, duplicate, and temporary variables such as dx, dy, and g in the slope calculation, all of which require constant space. Therefore, the overall space complexity is dominated by the dictionary, leading to n. To put this into perspective, consider the brute force approach. A naive solution would involve checking all possible lines formed by every pair of points and counting how many points lie on each line. This would require iterating over all pairs, which is n squared, and then checking all points for each line, adding another n. This results in a total time complexity of n cubed. By contrast, the current optimized solution avoids rechecking all points by using a dictionary to group points by slopes, reducing the time complexity to n squared. In terms of case analysis, the best case, such as when all points are identical, still requires iterating through all pairs, giving n squared. Similarly, the average and worst cases, where points form distinct or unique slopes, involve n squared iterations and dictionary updates. Mathematically, the quadratic growth arises from the nested loops, where the total number of iterations is the sum of the first n1 integers, or n1 asterisk n/2. Since dictionary operations and slope calculations are 1, the time complexity remains n squared, while the space complexity, determined by the size of the dictionary, is n. When solving the max points on a line problem, there are a few common mistakes to watch out for. First, vertical lines are often mishandled because their slope is undefined, which can lead to division by zero errors or incorrect grouping of points. To address this, treat vertical lines as a special case, perhaps by assigning them a unique identifier like infinity. Next, floating point precision issues can arise when slopes are represented as decimal numbers. Since floating point arithmetic isn't precise enough for long decimal expansions, it's better to use a rational representation like dy/dx, reducing the fraction to its simplest form. Another mistake is failing to account for duplicate points. If multiple points share the same coordinates, they should all be counted together when determining the number of points on a line. Forgetting this step can lead to undercounting and incorrect results. Now, a couple more mistakes to avoid. Overcomplicating slope calculations can trip you up. Instead of working with unreduced fractions like 2/4, simplify them using the greatest common divisor, GCD, to get 1/2. This ensures equivalent slopes are treated as the same, which is crucial for accurate grouping. Another pitfall to avoid is using inefficient nested loops. A naive O(n)³ approach, where you check all pairs of points against all other points, is far too slow for larger inputs, especially since the constraints may include up to 300 points. Instead, aim for an O(n)² solution by leveraging a hash map to group slopes efficiently. This improvement will save you both time and computational resources while still covering all necessary cases. When tackling this problem in an interview setting, there are a few key strategies to keep in mind. Start by asking clarifying questions, such as, how should I handle vertical lines and duplicate points? This ensures you're aligned with the expected handling of edge cases from the beginning. As you work through the solution, highlight patterns like using hash maps to group points by slope and representing slopes as irreducible fractions for consistency. It's also important to consider all pairs of points to guarantee that every potential line is evaluated. For optimization, use a hash map to store slopes relative to a fixed point, then calculate the maximum points on any line through that point. Iterating through all points as the fixed point gives you an efficient O(n)² approach, which is both practical and effective. This problem is connected to several others that can help deepen your understanding of similar concepts. For instance, LeetCode 146, LRU cache, focuses on efficient use of hash maps and caching strategies, which are fundamental to this problem's optimized approach. LeetCode 356, line reflection, deals with geometric properties and symmetry, offering additional insight into working with points in a plane. LeetCode 1499, max value of equation, emphasizes optimized pair evaluations, which parallels the idea of reducing computational complexity. Finally, LeetCode 1232, check if it is a straight line, revolves around basic slope calculations for all points, making it a simpler problem to practice foundational concepts before tackling this one. There are several approaches to solving this problem, each with its own trade-offs. The brute force approach, with a time complexity of O(n)³, involves checking all pairs of points and counting the points on each line. While this method is conceptually simple, it's computationally expensive and impractical for larger inputs. A more efficient solution is the optimized hash map approach, which operates in O(n)² time. Here, slopes are stored in a hash map relative to a fixed point, and careful handling of edge cases like vertical lines and duplicates ensures accuracy. An alternative, though rarely used, involves using polar coordinates to calculate angles instead of slopes. This method avoids slope-related precision issues but introduces new challenges, such as the complexity of trigonometric calculations. Each method has its place, but the hash map approach strikes the best balance between efficiency and practicality for this problem. Great job! We've successfully solved the problem using a hash map and an efficient approach to track slopes between points. Remember to practice applying similar techniques to other problems involving geometry and data structures. Thanks for watching, and I hope to see you in future problem-solving sessions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!